In this video, we are going to talk about the Hardy-Weinberg practice problems on the back of your Chapter 11, Section 3 and 4 PowerNotes sheet. So you want to make sure you have that sheet in front of you. You want to have a calculator so that you can calculate the answers to the questions on your own, and then you can check your work with the video. So we're starting here with question number 1, and it says 98 out of 200 individuals in a population express the recessive phenotype. Now remember, in order to have a recessive phenotype, there is only one genotype that you could have, and that would be 2 recessive alleles, or lowercase a, lowercase a. The question is then asking, based on that information, what percent of the population would be heterozygotes? And again, just to review, heterozygotes are capital A, lowercase a. In order to solve this question, we need to start first with our homozygous recessive genotype, which is Q squared. This is the information that was given in the question. 98 out of 200 individuals have the recessive phenotype. The recessive phenotype is equivalent to that homozygous recessive genotype, which in our Hardy-Weinberg equation is the Q squared term. So Q squared for this question equals 98 out of 200. So if you put that in your calculator, 98 divided by 200 gives us 0.49. So this is our Q squared value. Now, if you know Q squared, it is very easy to solve for Q because it's just math. If we have Q squared equals 0.49, we take the square root of that. That will give us Q. And if you would like to use your calculator, you can probably do it in your head, but if you'd like to use your calculator, you can. The benefit of using the calculator here is we are taking the square root of a decimal, and so sometimes it's really easy to put that decimal point in the wrong place. So our square root here is 0.7, not 0.07, so don't make that mistake. Again, use your calculator if you need to, but 0.7 is our value for Q. All right, step 1 is done. Next, now that we have Q, we need to solve for P. Remember, P and Q are the 2 alleles in the gene pool. If we know 0.7 or 70% of them are Q, which is recessive, then that means the rest of them must be dominant. So in the Hardy-Weinberg equation, P plus Q added together will always equal 1. Your dominant allele frequency plus your recessive allele frequency always equals 100% of your population. So that means P plus Q is 0.7, so let's put in 0.7 equals 1. Now it's just a matter of solving for P. So we subtract 0.7 from both sides and we get P equals 0.3. Now we're really getting somewhere. We have Q and we have P, and because we have those 2 variables, we can figure out any other thing that we need to from that Hardy-Weinberg equation. So remember, the Hardy-Weinberg equation is P squared plus 2PQ plus Q squared equals 1. P squared would be the frequency of homozygous dominant genotypes. 2PQ is the frequency of heterozygous genotypes. And Q squared, which is what we started with, is the frequency of homozygous recessive genotypes. Now our question is asking for heterozygotes, so that is the 2P squared part of our equation. So if we take 2 and we multiply it by P, P is 0.3, and we multiply it by Q, which is 0.7, again, go ahead and put that in your calculator if you're not sure you're going to do it correctly. I've already got 0.7 in there, so I'm going to multiply that by 0.3, That's 0.21, but don't forget the 2, so we're going to multiply that by 2 as well, and gives us 0.42. So 0.42, or 42% of our population is heterozygous, or capital A, lowercase a genotype. Now that's what the question originally asked us for. If we go on in part D, it's asking if now can we figure out the percent of homozygous dominant? Well, we certainly can, because remember the dominant allele frequency, or P, equals 0.3. So homozygous dominant is P squared. P squared, if we square this, we get, and again, check it in your calculator, 0.3 squared equals 0.09. Okay, so be careful there. 0.09. It's not 0.9 because 0.3 times 0.3, we have 2 decimal places here, so it's 0.09. And that will be the answer for this last part, the percent homozygous dominant. So in this first question here, our key to solving it was starting with Q squared, then getting Q, then getting P, and then we can plug in P and Q as needed in any part of this equation to get the answer that we're looking for. So before we move on to question number 2 here, now that we've done that first question together, I'm going to encourage you to stop the video, work through these questions, see if you can figure them out on your own, and then play the video and check your work. All right, hopefully you had enough time to do those calculations. If not, go ahead and pause the video before you check your work here. Your original population of 200 was hit by a tidal wave and 100 of your organisms were wiped out. So we have 36 homozygous recessive in 100 surviving individuals. Okay? We're assuming that the individuals were equal likely to be wiped out, meaning there wasn't any natural selection happening here. It was just random chance that caused some of them to be wiped out and some not. So now we're trying to figure out how the tidal wave affected those predicted frequencies in our population. We can keep using the Hardy-Weinberg equation here because it tells us the new population after the event is still in equilibrium. So anytime the population is in equilibrium, it is okay to use the Hardy-Weinberg equations in that case. So for this question, again, as always, we're starting with what we know. Homozygous recessive. So the frequency of homozygous recessive, it tells us we have 100 survivors, 36 of them were homozygous recessive. So 36 out of 100 survivors gives us, this is easy to calculate in your head, 0.36. And let's go ahead and say what variable that is. Homozygous recessive is our Q squared in the equation. Okay, next to figure out heterozygotes, what do we need for heterozygotes? Well, remember our Hardy-Weinberg equation, heterozygotes are 2pq. So we need to know P and we need to know Q. So in this question, we just figured out Q squared. Let's go ahead and take the square root of that to get Q. Now, if you want to double check here, we are taking the square root, oops, get the right button here, square root of 0.36 gives us 0.6. So we know that the square root of 0.36 equals 0.6, and that is Q. We're not there yet. That's not heterozygotes. Heterozygotes are 2pq. So if we know that Q is 0.6, 1 minus Q equals P. right? So we get 0.4 equals P. Now we know P, we know Q, so we can figure out 2PQ. So 2 times 0.6 times 0.4 gives us 0.48. So the answer to this question equals 0.48, or 48% of our population would be heterozygous after the tidal wave. Homozygous dominant. What are we looking for? We're looking for P squared. Well, we just got P, so if we square it, let's again double check our math. We have 0.4 squared equals 0.16. So we will write that as our answer for P, and that's 16% of our population. So part D, given that the allele frequencies did change as the result of the tidal wave, would we say that microevolution has occurred? If the allele frequencies change, by definition, we say that evolution has occurred. So would we say that it has occurred? Yes, definitely. And why is that? It is because the allele frequencies changed. Remember, we define evolution as a change in allele frequencies over time. That happened, so evolution happened. Now, what do we call the phenomenon that caused this evolution? Remember, this is a random event, so it's a type of genetic drift. And specifically, this is an event that wiped out half of our population and left the other half. So this is going to be an example of the bottleneck effect. The bottleneck effect is a type of random allele frequency change, so it is a type of genetic drift. So genetic drift would not be a wrong answer here, but bottleneck effect is a more specific answer. All right, go ahead now and look at questions 3. Go ahead and look at 3, 4, and 5, because now we've done 2 examples together, and then you can unpause the video after you've made your calculations and see if you got the correct answer. All right, so let's go ahead and take a look at the last few questions here. Hopefully you've already calculated your answers and you are just checking your work. So now we have brown fur coloring is dominant to gray. We have 168 brown mice, and we are trying to figure out the predicted frequency of heterozygotes. Okay, so we need to figure out our starting point first, right? Brown is dominant to gray. So what we want to start with is our gray mice, because that is going to be our homozygous recessive genotype. If we have 168 brown mice, we can't start directly with that because brown is going to be P squared plus 2PQ. Now, why do I say that? Because both of these would have a dominant allele in the genotype, and because brown is dominant, we can't just take the square root of this and say it's P squared, because our heterozygotes would have the same phenotype of brown. We need to start with gray. So what I would recommend here is, in our question, it tells us 168 are brown out of the 200. So let's take 200, subtract 168, and that gives us 32. So we have 32 mice that are gray, okay? So we did 200 minus the 168 equals 32 gray mice. Now we can say that 32 out of 200 is going to be our Q squared. So let's go ahead and take 32, divide it by 200, and we get 0.16. So 0.16 equals Q squared. That means if we take the square root of it, take our square root of 0.16, and we get 0.4 as the answer. So Q equals 0.4. If we know Q is 0.4, can we figure out P? Yes, because they must add up to 1, so P would be 0.6. So we kind of had to work in a big circle here. We were given dominant phenotype. We had to subtract to figure out how many were recessive. We had to divide by our total size to get Q squared, and then we had to take the square root to get Q. Then we had to subtract from 1 to get P. But at this point, now we have P equals 0.6 and Q equals 0.4. So heterozygotes are 2PQ. And that means in this question, 2 times, remember P is 0.6. Oh, that's a plus. 2 times 0.6 times Q is 0.4. And we get 0.48. That is our frequency of heterozygotes. And you can leave it as a decimal. It's asking for the frequency. The frequency is the decimal number. All right, next, homozygous dominant. Homozygous dominant is P squared. We know that P is 0.6. Again, just to be sure, put that in your calculator. 0.6 squared is 0.36. So we can put that for P squared. Frequency of homozygous recessive, that is going to be Q squared. We already calculated that. It's right here, 0.16. So that is how you do question number 3. All right, let's look at number 4. 81% of a population is homozygous recessive. What does that mean? 81% is 0.81. Homozygous recessive is Q squared. So let's just draw a line here so we don't get confused. Q squared equals 0.81. Well, that was easy. We already know Q squared. We just have to take the square root of it, put that in the calculator. Our square root of 0.81, again, you can probably do it in your head. That is going to give us Q equals 0.9. If we know Q, can we figure out P? Yes, we can, because they have to add up to 1. P is going to be 0.1. And now we have P and Q. We can figure out everything from that. So the predicted frequency of homozygous dominant, that is going to be P squared. So 0.1 squared, make sure you put that in your calculator correctly. 0.1 squared is 0.01. So you want to have that decimal in the right place. There's our P squared. The frequency of heterozygotes, that is 2PQ. So we're going to use these numbers right here. 2 times P is 0.1 times Q is 0.9. Calculate that and we get 0.18. And our last question, the frequency of the dominant and recessive alleles. This is asking for P and Q. It's not asking for a genotype, the actual allele frequencies. We already have that. They are right here. So there is our answer for part C. The dominant allele frequency is 0.1. The recessive allele frequency is 0.9. That was the first thing we figured out was our alleles before we could do any of these genotype frequencies. Okay, and our last question here. If 51% of the population carries at least one copy of the recessive allele, that means 51% of our population, that's 0.51, equals one copy of the recessive allele means you could be heterozygous, so 2PQ, or you could be homozygous recessive. So 2PQ plus Q squared adds up to 0.51. Well, we can't calculate anything directly here because we have both a P and a Q that we need to solve for. So what are we going to do? We are going to say, well, let's remember that there's one more term here, P squared. It's the only thing left. P squared plus 2PQ plus Q squared equals 1. So if I go ahead and say 1 minus this number here, 0.51, that gives me the value of P squared. And again, the way that I know that is because P squared plus these two things adds up to 1. So P squared plus 0.51 equals 1. If we subtract 0.51 from 1, we get 0.49, and that is our P squared. So P squared equals 0.49. You can probably guess what we're going to figure out from that. P squared, we take the square root. So let's go ahead and take the square root of that, and we get 0.7 for P. Can we figure out Q? Absolutely, because P and Q always add up to 1. Q is going to be 0.3. So now we have enough to answer any question about this. So let's look at the questions that it's actually asking. What is the predicted frequency of individuals in the population that express the dominant phenotype? Well, guess what? That is P squared plus 2PQ. So we need both of those values, and we need to add them together, and that's going to give us the answer to this question. We know P squared. P squared is 0.49. We figured that out right here. Plus 2PQ. Well, we need 2 times P, which is 0.7, times Q, which is 0.3. Add that all together, and what we have, we've actually calculated this a bit earlier. This is going to be 0.42, right? 0.7 times 0.3 is 0.21. Multiply by 2, we get 0.42. So if you want to verify 0.49 plus 0.42 in your calculator, just to make sure you do it correctly, we're going to get 0.91. So that means here 0.09 or 0.91 is our frequency of dominant phenotype in this population. Again, because it's asking for the dominant phenotype, we have to look at our two genotypes. We have to look at homozygous dominant and heterozygous and add those together to get the total frequency of any individual showing the dominant phenotype. Next question, what is the predicted frequency of individuals in the population that express the recessive phenotype? Well, the recessive phenotype, remember, that is Q squared. So these two terms were the dominant phenotype. The only thing left is our recessive phenotype, Q squared. We know Q equals 0.3. So if we square 0.3, we get 0.09, not 0.9, but 0.09 as our answer. And that is going to be all of the questions on this practice sheet. So if you didn't get any of these correct, if you still have questions about anything on this handout, please make sure you ask those questions in class. This can be something that's very difficult to get the hang of at the beginning, but the more practice you do, the easier it gets. So hopefully you found this to be helpful. And if you have questions again, or if you missed any of these, make sure that you ask about them in class.